Yes,
Is that for all of North America or
this
just
is globally.
globally?
This is
Okay.
globally, yes. So many papers are focused, well,
On
either centric focused, either United States, Australia, whatever it might be. This one is a global focus, looking at using climate models, like that's all we've got, right? All we can use are different models that predict out, and when we run enough models and enough of them agree, then that gives them additional strength. When they're really diverged, then they have weakness. We believe that there's too much variability for them to be a predictor. So what they did was they used these models to first predict the past. That's how you can calibrate your model. I teach that in my fire modeling class. We got to calibrate the past first. Can we predict what happened in the past with this model? And they did find that whatever models they were using effectively predicted what had occurred in the past, which then gives us a little bit more power and buy-in to what their predictions would be for the future. So in the past, they were able to predict that precipitation drove fires. Coming into the 18th century, 19th century, when we had enormous amounts of development, of agricultural burning, of decreased indigenous burning, but a lot of land clearing, a lot of land use change, we saw more of an anthropogenic-driven fire regime, both for fire ignition in that early industrial era where we have a lot of land clearing, and then also into the 20th century where we have a lot of fire suppression. We were pretty effective over the last 100 years at putting out fires. One of the reasons, arguably, that you could say that we were effective at putting out fires was because fires were easier to put out. The climate was in a relative slump where things weren't as hot, they weren't as dry. Now, 100 years ago, we had quite a lot of fires in that 1910 era, these big fires. It wasn't uncommon to have these big fires. We did seem to have a dip in that fire activity, certainly because of fire suppression, but also because of just general climatic conditions. So one of the, like as I read papers, the thing that does get me a little bit is when it goes from 1980 to 2010. 1980 to 2010 is not the best to show this increase. It exists there, but when you just look from the middle of the century to now, there's other things going on that affected that increase. So getting back to this driving things, we've got precipitation a long time ago, anthropogenic in the last 100 years, and then what we're seeing right now and what we're predicted to see in the future is a temperature-driven fire regime. So we're seeing already increases in temperature, and that is correlating and expected to correlate additionally with increases in fire occurrence. That has a big influence on, well, the way that what drives fire occurrence is what we then have opportunity to respond to as fire managers. We can respond to anthropogenic fire. We're pretty good at that. We've done that for the last 100 years. We can respond to human ignition, and we can respond to buildup of fuels because of fire suppression. But we are ill-equipped to respond to a temperature-driven fire regime. The techniques that we've applied in the past are not going to work as good. And we need people that are more capable of making a different type of decision on the ground than what we currently have. This is, I guess, for my education, have more people that are educated in fire management comes in. But really, I don't just sell that because it's going to keep me in a job, which it is. But we do have a diverging a time right now to make a different set of decisions in our fire management and to give more empowerment to different ideas. And that's a really hard thing to change. Just as I'm carrying on about this, I did go into some of these numbers. We often think about wildfires as, we're US-centered. Generally, we're pretty US-centered. Wildfires in the United States, according to one source, make up 5 to 10% of the CO2 emissions.
Say that again.
Wildfires in the United States account for 5 to 10% of CO2 emissions. So we recognize, I think we're pretty comfortable at saying climate change is going to affect wildfire, but wildfire is going to affect climate change too.
Okay.
And globally, we have actually observed a decrease in fires. So sometimes, so in the United States, on the news and all these things, all these houses burning, we feel like, man, things are really, really blowing up. But we do need to recognize that we're just a piece, and also the piece that we see might not be totally representative of what is actually occurring all the time.
Does that include agricultural burning, say in Indonesia or South America?
Yes, it does. So this instance, it was including that. So we have, when things are initially cleared, because of land use change, there's burning. But after that, there then is less burning because it's then used for agriculture. And so there's going to be back and forth, especially depending on the practices at the time. But at least according to this source there, globally, we may see a decrease in total fires because of the increased amount of people or the type of use of the land, rather than it being more natural vegetation, being more agriculture vegetation.
So this is considering all the stuff nature did back when, as well as now the man-caused
Right,
stuff. Okay,
right.
okay.
So you're probably seeing this cycle, right? Warming, fires, fires, warming, warming, fires, fires, warming. Because there's no direct answer, and sure, conceptually, CO2 goes up into the air, increases global warming. There's also the opposite effect. Fires can sometimes create cooling in an area, just to really muddle your the things that you might develop opinions on. When in fire management, for example, you're right here, when there's all this smoke in the air, you have a very actively burning fire. You have a high pressure system come in, it pushes all that smoke down, and then you see a decrease in fire behavior. And so the columns that are produced by these fires actually limit their ability to grow. So there is a feedback cycle in that way, certainly. And then there's also chemically in the atmosphere, there are cooling properties of the smoke that is put up into the atmosphere. There's cooling properties of that smoke that can impact large atmospheric weather systems. On the converse, just to flip back and forth again, you have a lot of atmospheric particulates that are put up into the air from all this burning stuff. Those can go very far distances. They can fly all the way to these big ice sheets, and they make that ice sheet a darker color, and that absorbs more heat, and it melts the ice sheet faster. So the world is all about this balance, and that balance has always existed. There's always been a little bit of this and a little less of this, and what we are generally finding through research is that the ultimate pattern is that there is going to be more warming than there is cooling. Also, across, when we begin running these models that are predicting these different changes, there's several different models that predict how that's going to impact globally this world, and there are some places that will receive less fire and some places that will receive more. And the severity of it, the location of those things is generally in question, but for example, the East Coast is expected to receive, or to have a less frequent fire return interval, less frequent fire, less intense fires there, and the West is expected to receive more. That might not be surprising to us because we think, gosh, what's going to burn in the East? There's like so many people over there, like they'll put that fires out right away. But historically, the fire return interval on the East Coast has been relatively frequent. It burns when those leaves are off. Obviously, when the leaves are on, it's not going to go very far because things are so wet. But fire is absolutely a part of that ecosystem when the leaves are off and things are things are dry in the spring and the fall. Probably more in the fall than the spring. But so point being that we are expected to see diverging responses to our fire situation, depending on where you're at. What we are noticing when we are observing these patterns and changing fire is that we're observing changes in vegetation, a condition. Timbered areas become grass areas become desert areas. When, for example, in the Jemez Mountains of New Mexico, the ponderosa pine regime, the vegetation that's been there for as long as we can recognize, relies on that frequent low-intensity fire. So then you get a high-intensity fire that comes in, kills those overstory trees, not the end of the world, not totally unheard of. The seedlings come up, they're about 10 years old, they need to be 50 to make some seeds. And then another fire comes in, and it kills those seedlings, and now you have grass. It seems shocking, it is shocking, and you see that pattern in lots of different places. In Australia, their alpine ash is disappearing. It's a very highly adapted fire species, and it's going away because it's getting too much fire. Stuff changes, but this is big change, and we're seeing it over huge, huge swaths of area. The other contributors that add to that effect are invasive species. So in the chaparral ecosystem, for example, the typical fire regime for chaparral is 50 to 150 years, pretty far. We think of fire, or we think of California, we think burning all the time. It didn't historically burn all the time. Some places did. Southern California probably had more volatile, more frequent fires. But it was limited because of its vegetation. It didn't have enough vegetation to carry fire from one place to the next. With the increase of invasive species like cheatgrass, all of a sudden the dots are connected. You have vegetation, nothing, vegetation. It's going to take a while for fire to reach from one thing to the next. You'll have to have a big wind event, you'll have to have really dry. When you have vegetation, vegetation, it's going to carry right over that. Add to that increased fire occurrence from humans, from human ignitions, and you all of a sudden have a totally altered fire regime. Now we're getting fires every 5 to 10 years because the vegetation's there and the ignitions are there. Just because things are hot and dry doesn't mean that you're going to have fires. You have to have an ignition source to have that happen. I wish I had a statistic about how many ignitions are from humans, but a fair amount, with either arson or power lines, or just chain dragging along the road. When you have people, you have more ignitions. And then that, of course, changes the vegetation regime that's there. I'm going to take some other questions. I can talk all day about this. You can have students that have that. Lauren.
Heather, you talked about the release of carbon dioxide from fires. How much of that carbon dioxide is reabsorbed when you have regrowth of the forest? Because you've got a really actively growing forest when those seedlings come in. And start
Very
to
good
grow.
question. Yeah, you're right. So we definitely see a huge influx of carbon dioxide when things are burned. You take all that carbon that's stored up in those trees and you just shoot it off into the atmosphere. But after the fire comes through, you have all these nutrients, all these animals that love those fires. They just eat those little ice cream branches up. You know, they just go in there and they just have a great party, eating all that good stuff. And they grow fast. And that reabsorbs a lot of that carbon. That's a huge opportunity for that to reabsorb. But what if we see a regime change? If we take out that timber and we go to a grass model, our capacity to absorb a lot of that carbon, it really decreases. Now those are in those edges, like so a species exists in a bell curve. It exists healthily in this middle ground where like at this elevation, at this precipitation, and it exists unhealthily in these edges. It's either weak because it's too wet or it's weak because it's too dry. So what we're starting to see is this bell curve shift, where areas that were originally, when those seeds established, were very suitable and in the middle of that bell curve for that species, are now toward the edge of that bell curve. And when they're removed from it, then they're no longer able to grow there because it's not as hospitable of a place.